Okay. Good afternoon, everyone. Thanks, first of all, for the opportunity to come up here and speak to you. It's going to be a bit of a gear change, I think. My talk is a little bit more focused on how we actually use Sequent products, but hopefully you'll enjoy it. All right, this is actually a much shorter title than the original one. It was much wordier, but we managed to cut it down. I don't think it would have fitted on the slide. But take a good look at it because we're going to talk about all of those things in a bit of detail. So we did have some individual brilliance will only get us so far, and how collaboration is really important to what we do. Anglo American has a problem. It's a wonderful problem to have. We have significant endowment, and we have some commanding tenure positions in various parts of the globe. As a result of that, our long-term resource development planning engineers have a not inconsequential task of providing some strategic direction as to how we should best spend our exploration and hopefully mine development dollars to try and maximize the latent value that sits in these tenure positions. In some cases, those tenure positions carry mineralization and in some cases mine plans out more than 100 years into the future. So we're talking about significant things. Along with having those kind of tenure positions and those kind of land holdings comes a responsibility. And part of that responsibility is a vision, and that vision is a complete description which honors all of the available data. It also incorporates all of the current geological hypotheses that we may have around those endowments. And what we want to do with them is then create these viable alternatives that broadly capture the geological and grade uncertainty that we know sits in these positions. We obviously don't have a lot of drilling information or other types of information in some of these, given the size of them, but we still want to have an understanding of what we may actually have. It's an older slide, but I think it's a good one. So this is what how we categorize our endowment, and it has an iceberg shape, and that's not by accident. On the top, we have what we can report, so that's our mineral resources and reserves, and those obviously abide by very strict codes, SAMREC, JORC, etc. And underneath that, what we have, what we call below the line, are the things that we only report internally, but really encapsulates what our endowment is. As part of that, we have these progressively relaxed criteria about how we describe them and what we can do with the information. And in fact, as we go further down, and I'm talking mainly about that light blue part there, the quantified non-inventory, so they're still spatial block models, but we prefer to describe them and report them internally in terms of ranges because that's the kind of precision that we have on the data. The way that we do that, and I know that we're probably a little bit behind the oil and gas industry, which is doing this kind of thing for a couple of decades. So we are a little manual in the way that we're doing it at the moment, but it's still a big step forward from the way that we were doing it, say, 5 or 10 years ago. And we've come up with what we've actually called a matrix of alternatives. On the y-axis, we've got these hopefully equiprobable geometric alternatives, which encapsulates all of the geological uncertainty. And then on the x-axis, we've got some kind of grade variance. Each of these then becomes a case. So in here, we've got 9 cases. But of course, according to the curse of dimensionality, the more axes you add, the number of cases that we could be considering explodes exponentially. Being part of a large diversified mining company comes with its own set of problems. One of them is not the fact that we don't have skills. We have a huge amount of highly skilled people. The problem is a lot of them are spread all over the world, which means they're spread across different time zones. So getting them in a room, virtual or real, can be quite difficult at times. And in order to be able to answer the questions that we have in our endowment and create these models that I've just talked about, we need to have some way of being able to get them together and being able to leverage from all of their different skills. So what is the approach that we've taken? It's collaboration. Now, I know that was the theme from last year's Lyceum, and I wasn't here for that, so I thought I'd just reuse some thoughts that I had that I wasn't able to share with you. So I started doing some research into what actually collaboration is. The first thing that came up was traitorous cooperation with the enemy, which is not really what I had in mind, even though when I'm dealing with engineers, sometimes it does seem like that. My apologies to engineers in the audience. So collaboration is actually what occurs when two or more people work together to realize some kind of shared goal. There is always an element of leadership that happens when there's collaboration, but it's generally, it doesn't have to be hierarchical, it can be decentralized and more egalitarian. In addition to collaborating, we would like to work in an agile sense. For those of you who are not familiar with what the agile terminology or process is, it's really an approach to developing a product of any type, where it evolves through collaborative effort, generally through these kind of self-organizing or cross-functional teams. In a geoscience context, what that means is instead of doing a complete drilling program, waiting for the results, saying, yes, this drilling program results are okay, and then cascading those down through a traditional resource estimation workflow, which may take 18 months to 2 years from the time that the drill stopped turning to when the engineer actually gets a block model. We want to reduce the size of each particle of information running through a system and have the system connected end to end, such that the model updates are happening all the time. And what that does is it allows evolutionary development, early delivery, which was a big one. My boss in the audience knows all about not having early delivery, so we wanted to fix that this year. And then continual improvement. It also allows the customers at the end to be able to provide some input into what's going on. Probably the most important thing in the geological sense from the agile modeling approach is that it allows conversations in the face of uncertainty. As I described earlier, we have issues when it comes to geography. Issues with geography carry with them issues of culture. In a highly hierarchical culture, it's very difficult for a rig geologist to offer up a differing opinion on a result that may have come to his more senior or her more senior boss. So having some kind of solution where we can collaborate and we have some kind of nucleus, it breaks down barriers and allows people to be able to have the conversation where they're able to say, I don't agree with that bit over there, or I don't think this bit is right. And it allows and actually feeds the evolution of those models. In a true agile sense, there is no final model. Obviously, when we have to deliver something and report the resources and reserves, there has to be some final version. But it is something that does evolve over time. So I've been talking about workflows, and now I'm going to talk about the bits where Seequent comes in. So of all the things that I've described before, wanting to be agile, wanting to collaborate, we needed a solution that was going to allow us to be able to create those endowment models, that full matrix of models, and follow through the agile collaborative approach. Ideally, we wanted to do it in one package, and we wanted to do that because in previous iterations, we had done part of the modeling in one package, generally Leapfrog, and then we'd had to export it to another package to run some estimates, and then messing around. And it made the interfacing, specifically with large tenement positions, very unwieldy. So we wanted to try and keep it in one package. Leapfrog was the obvious answer to that. It also happened to be, it needed to be safely stored. No more C drives, no more thumb drives, no more portable hard drives. We needed to be stored and accessible across the globe. Central browser marked a really good opening into that. And it had to be easily accessible, so cloud-based and accessible through all of these different mediums. So the solutions that Seequent is offering seem to be offering exactly what we needed. In the title, I talk about cryptic geological environments. So by definition, in our endowment, we don't necessarily have a lot of information, and therefore we don't have a particularly strong handle on some of these mineralizing systems, which means that our knowledge is in its infancy, but it is rapidly evolving. As we continue to gather more and more data, what we understand about the systems is changing rapidly. And we need to keep this evolution moving. We need to continue to behave like scientists. George Box is often quoted and sometimes misquoted with this particular quote, which talks about how all models are wrong, and that the scientists cannot obtain a correct one by excessive elaboration, but following Occam's razor, we should seek an economical description specifically of natural phenomena. And we need to devise simple but evocative models. Now, I don't fashion myself as a great scientist, but I certainly don't want to be labeled a mediocre one. So I think this is an excellent formula to follow. when I was talking about the equiprobable alternatives up front, one of the things that becomes quite important is the stratigraphy and how we describe that. In an endowment, specifically when there's a large endowment position around a mature operation, you generally have two competing stratigraphies or mineralizing ideas that are put forward. You have an incumbent metal-centric one, which is generally some kind of grade shell plus lithology, excuse me, and that's generally focused on the deportment and distribution of the primary metal of interest. But as things evolve, as we gather new information, we may come up with some kind of new stratigraphy model, which is based on empirical data and observations, but hopefully has a more holistic focus. This is the kind of evolution that we've been going through with some of our endowment positions. This is a cross-section. You're going to see this cross-section a lot in different forms. What we have here is some stratigraphic sequence that's been modeled in Leapfrog. We have a single drill hole, and this is a fairly common thing. You have very little information, and you have some kind of model that you put together. What we know in this example is that there is some kind of brittle deformation, but we don't know whether there is actually any movement across that brittle deformation, and therefore having a rolling alternative is actually a viable geological model and something that we should investigate. On the other hand, since we know that these brittle structures are there, if you had to actually activate them and see what's possible, you could come up with something that's very different. And if you're considering different mining methods, if you were looking at an underground operation versus an open cut one, having that kind of movement across fault structures is obviously significant. But here, immediately, we have two very different alternatives. Once you have a geological volume that you want to consider, you still have to fill it with grades somehow. In endowment positions, you have vast distances that have to be grade filled with little or no drill support, and that poses significant and very well-known risks for downstream evaluation. So long search ranges, if you have to search up to kilometers for drill holes, you lead to over-smoothing, of course, which generates the well-known inaccurate estimation of tonnage and grade. In some cases, and in the case that I've got here, the reproduction of a vertical grade stratigraphy, for want of a better word, it's very important for valid mining and economic evaluation, but it can be very difficult to reproduce in rolling or faulted stratigraphies, especially if you have no data. So when the Edge module came out in Leapfrog and it had this new variable orientation, we got really excited. And it's a really, really good tool if you have data. If you don't have data, you're still kind of left where you started. But at least it offered us a possible entry into a one-package solution, which is what we were trying to get to. So what we did was we went and created a workflow that largely solved the problems that we needed to keep everything in one package and be agile and allow everyone to collaborate. What it is, we create a pseudo set of drill holes at some kind of spacing that's relevant to the problem at hand. You then evaluate your various geological model alternatives against that set of pseudo drill holes, export both the pseudo drill holes and your real data into some other nameless geostatistical package, and then use some kind of flattening or unfolding to a stratigraphical meaningful data so that you can analyze these things in a space that is more representative of the problem that you're trying to solve. We then perform Gaussian anamorphosis, spatial covariance estimation, and modeling, maybe an LMC or whatever happens to be appropriate on this unfolded and flattened data. Run some number of realizations, say 50, depending on what it is. And of course, here you're making an implicit assumption about what the geostatistical nature of the area outside of your drill coverage is. And of course, this is another thing that can be changed. I mean, if you take the most simple approach, you say, this is where we know how it behaves geostatistically. We're going to enforce that behavior and reproduce histograms and variograms in the areas outside of where we have drill data. But you don't necessarily have to do that. You can play around with that. Once you've simulated these and you have these realizations, you then rank them by some kind of useful metric. You could do something as simple as just a mean ranking, but you could use something much more sophisticated, Kolmov, Smirnov, D-statistics, Mahanolobis distances. There's lots of alternatives. You can then select some kind of meaningful realizations from the ensemble. So in our case, we chose a realistic one, and then a low ball and a high ball case to try and capture some of that uncertainty. Refold or unflatten that back to real space, append that to your real data, and you now have 3 different data sets that cover, at some spacing, your entire endowment. So we're just going to run through a couple of these cross-sections. So this is it. We've got our single bit of real data. We have, at some spacing, our synthetic data set. What I did was I just excluded drill holes a particular distance around our real data, so it wasn't swamping the real data. Appended them together, we now have 3 data sets at a spacing that we can now use Edge and the variable orientation tool and actually generate some kind of result that has the kind of grade granularity that is going to allow the downstream evaluation to actually make a realistic look at that. So that's the kind of thing that we see. So now I don't have a picture of where we have more informing data, but the kind of granularity of those grades and the orientation of them is a really good proxy, and it's a very good comparison to where we have large amounts of data. This is a highly assumptive process in terms of this behavior, but it is better than having something that's highly smeared. So going through this and really pushing Edge as a module to its maximum in terms of what's currently available, there are a bunch of really useful features that are in it at the moment. It is part of a deliberately agile workflow. Anyone that's worked with Leapfrog Geo knows that it is agile. You change something higher up in the hierarchy, and it'll flow through the entire model. So it is agile exactly as we need. It's relatively simple to extend to alternative cases. So on the right, you can see I've got a list in the informing data, and I've got all of our alternatives, a P10, a P50, and a P90. Once you've set up an estimator once, you can just go and select, right, I'm making the assumption that the variograms and search ranges and everything is still applicable to the higher and lower cases. That's assumptive once again. And I'm going to simply choose another data set. I suddenly have a completely different realization of that domain, which is a high ball or low ball case. During the process, I spent a fair amount of time mentoring and teaching, and Edge is a very good way of doing that. It's a very simple interface. It's object-based. It's really easy to use, and because it has good user interface and good graphics. It's really easy to teach the basic concepts that go into a resource estimate. We're entering a brave new world, and with that new world comes these new words: risk, uncertainty, big data, agile production. As a result of that, and I think all of us in this room will be well aware of the fact that our workflows are changing. How we define what a geologist does at any stage is a rapidly evolving thing. We know that moving into an agile development it's worked very well for us, and it's almost going to become a necessity going forward in terms of rapidly being able to change and reinterpret things on the fly. We know that is supporting a collaborative environment, which is where we need to be. And we've identified it as probably the best current method to leverage from all those skills that we have and to help us quantify the uncertainty and manage that risk. Thank you.